Chem 1A. This is Chapter 5, Lecture Video 2, and we're going to be discussing stoichiometry again, but this time instead of just going with moles, now we're going to bring grams and mass into the system, or into the problem. So most of the time when we're doing stoichiometry problems, calculating how much we form something, calculating how much we need to use to make a certain amount of something, we're not usually given the values in moles like in the last lecture video. Most of the time we're given them in grams because in the lab, that's most often the unit that we're measuring. Now because of this, we can't just immediately use a mole ratio. We first have to start with converting our masses to moles. And then once we're there, then we get to use our mole ratios, which we cannot do without a balanced chemical equation. Again, this is so important. So a general scheme of stoichiometry problems when they involve grams kind of flows like so. We start with grams of what we're given. We use the molar mass of that substance to get to moles. Then we want to change from the moles of the substance we're currently in to the moles of a different substance. We use a mole ratio to do that we get from the balanced chemical equation. Once we have moles of the new substance, sometimes we might just stop here, or we might continue on to get mass of the substance that we formed, which would mean then yet again using molar mass, this time for the new substance, to get grams of that new substance. So this is kind of a flowchart that is pretty much the general feeling of stoichiometry. First we use molar mass to get to moles, then we use a mole ratio to get from moles of one substance to moles of a new substance, and then we use the molar mass of that new substance to get grams of that new substance. So let's look at a problem. Here we have the combustion of ethane, right? We have C2H6, that's ethane, reacting with oxygen to form CO2 gas and water in the liquid state. This is a balanced reaction for us already, and maybe we want to go, okay, hey, how many moles of water are we going to make when we react 7 moles of oxygen? Well, this is kind of like the last lecture video. We have 7 moles of O2. In this case, we just need to do a mole ratio. 7 moles of O2, we know, go to 6 moles of H2O. And again, I'm getting these values here from the balanced chemical equation. And so we hit equals here, 7 moles of O2, the moles of O2 cancel, and we're left with 6 moles of H2O. Technically, if we're paying attention to our sig figs, this should be 6.0 moles of O2, H2O, that we formed. But what if we weren't given moles? Let's do the second question here. We have how many grams of CO2 would be produced from 23.4 grams of C2H6 reacting with excess oxygen. Now this excess part we'll get to in just a second. This basically means that this is what we'll eventually learn is called the limiting reactant. So in this case we have 23.4 grams of C2H6, and the first step here is we can't use grams initially with a mole ratio. We have to get to moles first. So we need to calculate the moles of C2H6 using the molar mass of C2H6. If we do that calculation, we'll get that the molar mass of C2H6 is about 30.08 grams per 1 mole of C2H6. Now I can use my mole ratio because as you can see here, grams have canceled and we're left with moles of C2H6. Now I can use the mole ratio. Now what do I want? I want grams of CO2. Well, first I need to get moles of CO2, so let's do our mole ratio. We know that 2 moles of C2H6, again getting that from our mole value in the balanced chemical equation, goes to 4 moles of CO2. Now you can reduce this fraction if you want to, it's not really that important. So if we look at this again, our moles of C2H6 have canceled. Now we're in moles of CO2. Now I wasn't asked for moles of CO2, I was asked for grams of CO2. Well, how do I get from moles to grams? I need to multiply by molar mass. Now the molar mass of CO2 is 44.01 grams of CO2 for every 1 mole of CO2, and here we can see our moles of CO2 canceling, and we're left with our grams of CO2. If we do these calculations out, we get that our mass of CO2 formed is 68.5 grams of CO2 is being formed in this reaction. And so this is a general stoichiometry problem. We could have asked for how many grams of H2O were formed from this mass of C2H6. I could have also asked how many grams of oxygen are reacting with 23.4 grams of C2H6. Number of different questions, really just those three actually, based on the starting value that we were given. All right, so let's talk about limiting reactants. Like with anything, if you run out of one of the things you need to make something, you can't keep making things, right? So in some cases, when we have two or more reactants in the reaction, generally one of those reactants will have less than the other present, which means it will run out first. We'll consume that one reactant before the other reactants, and the other reactants are going to stay in the system. There will be some left over. This reactant we call the limiting reactant, the one that runs out first, because it's the one that's going to limit the quantity of product that you can form. Because at the end of the day, if we run out of one of our reactants, the reaction stops happening and we don't make any more products. We always have to use the limiting reactant when we're determining how much products we actually made, because the other reactants, they're going to be able to make more if we had enough of the limiting reactant, but we don't. The limiting reactant's the one, again, that limits the supply of products, and therefore is the one that we use to calculate what we call the theoretical yield. More on that in just a second. So kind of give you an idea here. For each reactant, let's calculate how do we determine what the limiting reactant is. We take the amount of each reactant that we're given and we calculate how many moles of one particular product we can make from both reactants. Whichever one forms less product would be the one that limits the supply of product and therefore is the limiting reactant. And that's the mole or mass value that we use to do our calculations. The limiting reactant is always the one that's going to give us fewer moles of the chosen product, and we'll do an example calculation in a second. The other reactants, the one that could form more product if we had enough of the other reactant, the limiting reactant, are what we call in excess. So if you're told in a problem that this reactant is in excess, then the other reactant is by default our limiting one, and we don't even need to figure it out. So let's do an analogy here. How many sandwiches can we make if we have 6 slices of bread, 6 slices of meat, 6 pieces of lettuce, and 6 tomatoes? Now we have a specific recipe that we need to follow for our sandwich making. We're going to use 2 slices of meat per sandwich, 2 slices of bread per sandwich, 1 piece of lettuce, and 3 slices of tomatoes. All right, so how many sandwiches can we make based on these ingredients, right? Well, we're going to assume this is 6 slices of tomatoes, and that basically tells me that I can make exactly what? 2 sandwiches, right? Because I have 6 tomato slices and I need 3 tomato slices per sandwich. Well, if I make 2 sandwiches, I'm out of tomato slices. I still have leftover lettuce, meat, and bread. I could make more sandwiches if I had more tomatoes. But tomatoes limit my sandwich making, and therefore in this example, tomatoes are my limiting reactant. Now, after this, that's the one that runs out first. If we have other stuff left over, right? We have 4 pieces of lettuce left over. We have 2 slices of meat and 2 slices of bread still remaining in our kitchen, I guess. All right. Okay, so let's continue on. So actual and theoretical yield, these are two vocab words that we really need to understand. So theoretical yield is the maximum product yield that can be calculated based on basically stoichiometry, what we've been talking about. So when you calculate how much product you made using theory, or in other words, these theoretical calculations, stoichiometry, that's a theoretical yield, because at the end of the day, that's assuming everything went perfect when you went and did the experiment. In reality, things don't always go perfectly, and almost they never go perfectly. So the actual yield is what is actually experimentally measured, right? So great, we did these theoretical calculations. We should be able to make 5 grams of this product. Great, you go and you do the actual experiment, you only make 4.5 grams. That's your actual yield. The theoretical would have been whatever you calculated it was going to be, right? Actual yield is what you actually measured when you did the actual experiment and you ran the reaction. The percent yield kind of gives us a report card for how well we ran our chemical reaction, right? The higher the percent yield, the better we did. And it's really just a comparison of the actual yield and the theoretical yield. So you went away, you measured your actual yield, you calculate your theoretical yield. We're going to divide these two values, multiply by 100, and that gives us our percent yield. What percent of the theoretical yield did we actually make? That's effectively what the percent yield is. Now, you can do grams or moles for these two values in the equation, but it's very important that if you're in moles in the top, you got to be in moles in the bottom, and if you're in grams in the top, you need to use grams in the bottom. You can't mix and match units. Okay, so actual yield usually is less than your theoretical yield. This is due to a number of reasons, such as impure reactants. Usually in chemistry labs, we use 99.999% pure reactants, but there's still that 0.001% there that is a little bit impure. So it might affect your results very minimally. That's not a usually big one. A bigger one is you have byproducts going on, right? In organic chemistry, you'll find that a lot of your reactions produce all these side products that you weren't expecting. Well, if you're making those extra products, you're using up your reactants to do that. You're not going to form as much as you thought of the major product. Sometimes we have reactions that don't go to completion. We talked about equilibrium in chapter 4 very briefly, but if a reaction goes to equilibrium, it won't go to completion, and stoichiometry pretty much assumes that our reactions go to completion. So this is more often than not one of the bigger reasons why our actual yield ends up being less than theoretical. All right, so let's do a calculation here. We have what is the limiting reactant if we start with 50 grams of aluminum and 50 grams of oxygen. So I have 50 grams here of Al and I have 50 grams here of O2. Now I do not know which one of these two things is my limiting reactant. I need to figure that out first. And the way we do that is we're going to take the two reactants, pick whichever one you want to start with, and we're going to go to how many moles of one of the products in the reaction, and we just got to use that same product both times to figure out how many moles of product we can form from that reactant. Now, in this case, we only have one product, so obviously we're limited to Al2O3, but if we had two products, you just pick one and use that one for both calculations. The next step is, converting grams to moles of that product. This is effectively stoichiometry. So we have grams of aluminum. The first step is to use the molar mass of aluminum to get to moles of aluminum. The molar mass of aluminum is 26.98 grams of Al per 1 mole of Al. Right? So next we use a mole ratio. I know that 4 moles of Al, again this is from the balanced chemical equation, gives me 2 moles of Al2O3. And next I'm back to molar mass. Now I need to use the molar mass of, at this point we can just hit equals and get what our moles of aluminum oxide is. And we're just going to stop there for now on this number. So once we calculate this, let's calculate. We get that you get about 0.927 moles of aluminum oxide formed from the aluminum in the system. Well, let's do this again, but now we're going to do it with oxygen, right? So I have 50.0 grams of O2 as well. The molar mass of O2 is 32.00 grams of O2 per 1 mole of O2. And I know that the mole ratio here in this case is going to be 3 moles of O2 goes to 2 moles of Al2O3. And we can calculate how many moles of Al2O3 we can form from this calculation. And it gives me about 1.042 moles of aluminum oxide. Now, if we look at these two, which one produced less? It was definitely the aluminum that produced less moles of aluminum oxide. At this point, we have exactly no use for this value. The larger value, the value calculated from the excess reactant, is useless. We do not use it anymore other than just for comparison's sake. And we're pretty much done with it. So let's look at the next question, right? Because at this point, we know that aluminum is my limiting reactant. We're also asked what the theoretical yield for the reaction is. Now, in this case, we actually already answered it. You can report theoretical yields in either moles or grams. It just depends on what you want to do. In this case, I could stop at moles, or we can multiply by the molar mass of aluminum oxide to get grams. And if we do that, 101.96 is the molar mass of Al2O3, and we're going to get that we have about 94.5 grams for our theoretical yield. Okay, so one last problem. What if we know that when you ran the actual reaction, you only collected 48.5 grams? What's the percent yield then? Well, this is our actual yield. Here's our theoretical. So our percent yield is going to be equal to 48.5 grams divided by 94.5 grams times 100. Which gets me a percent yield of about 51.3%. All right, so if you have any questions, as always, please let me know, and see you in the next lecture video.